I is proportional to a square with some equation 2 pi rho v a square v square, we can have the equation for, we can have the value for I, and using this, say this proportionality, we have found that I0, the minimum audibility level, is equal to 10 raised to minus 12 volt per meter square, right? So this can be used to define one another level, say it is L0, the absolute loudness level, or say the level with respect to which we can find out the L, that can be L0, and which is dependent on I0. So now L0 is equal to K log I0, and since we have L1 equal to K log I1, so what will be delta L? Delta L is equal to L1 minus L0, that is K log of I upon I0, right? And this K log I upon I0, when I take K equal to 1, delta L, or say loudness level, or IL, different books have different symbols, IL will be equal to log of I upon I0, right? This is called 1 bell of loudness. But when I say that, since I said that bell is a very big unit, I'll have to divide it by 10. So when I take K is equal to 10, delta L will be equal to IL, that is equal to 10 log of I upon I0. And generally this is the well-known equation to find out the relative loudness in dB. So 1 dB equal to 1/10 of bell. Bell is a loudness unit, and it can be measured, the loudness can be measured in terms of decibel. Whenever you use any of the electrical equipment, you may have say it may be a speaker or it may be a television, the maximum limit they have said, they have actually in their manuals they write that this is the maximum limit up to which it can be, this instrument can be run, and this is the maximum limit up to which you can hear. Actually we have talked about the threshold of intensity and threshold of pain. Threshold of intensity says we have taken I0 as the minimum intensity level, that is 10 raised to minus 12 volt per meter square, right? We have told that I0 is the minimum level that we can take. It is 10 raised to minus 12 volt per meter square, which is equivalent to 20 Hertz frequency, which is equivalent to 0 dB. One can see on the slide, right? This is called threshold of audibility or minimum audibility level, and threshold of feeling or say threshold of pain is 20 Hertz or say 20 actually 20 kilohertz, the maximum audibility level, or it is equivalent to 120 dB, right? That is actually the I max, threshold of equivalent to I max, threshold of pain or threshold of feeling. Okay, so the smallest, one more physical fact about the intensity level or say loudness level is that the smallest change in the intensity level that the human ear can detect is 1 dB. A change in intensity by 26% increase the intensity level by 1 decibel, and this can be proved through two cases. We can take again on the tabletop to just prove this with a simple calculation. If I take case 1, case 1 says, again I am putting this equations, the values that I take, that I will put in the same equation, 10 log of I upon I0, right? So say if I am taking IL equal to 0 dB, what if I put this value in the above equation? I'll get it what? I'll get 0 is equal to 10 log of I upon I0. This will result into I is equal to I0. But in case 2, I'll take IL or delta L equal to 1 dB. I am increasing the decibel level by 1 level, and this will give me the result I is equal to 1.26 I0. So this 26 plays an important role in a way that the intensity level or loudness level is not linearly proportional to I, it is logarithmically proportional to I. If you increase your loudness level by 1 decibel, by 1 unit, then the increase in intensity will be by 0.26% or say 0.26 times or say 26%. The smallest change in the intensity level is that the human ear can detect is 1 dB, and the change in intensity by 26%, that is proved that intensity level will be changed by 1 dB. Now this is a well-known saying that sound is a much part of man's man-made environment as heat or light. It is actually the essential part of the man's life, and it can now be effectively managed, notably in room when music is heard, by applying the principle of acoustical physics, or say architectural acoustics starts here. Now with all the things that we know about this, we can now think about the interaction of sound with matter. There are 3 ways. First is the sound source is, the sound is reflected, another is transmitted, and the second one is absorbed. Here, while designing a good building, we are dealing with 2 major things here, 2 major phenomena. First, the reflection, another is the absorption of the sound. Now, what will be, first if we take the reflection, what will be the first reaction when we think about the reflection of sound? That is the echo. Whenever you have moved to an hilly area or in a large room of your college or in a large foyer or even in an empty cinema hall or even in an empty mall, you may have experienced the echo, right? Or even in a temple or mosque, when you are there, you hear something which is not pronounced or which is not spoken by you, right? So that echo, that is called echo. It is produced when the sound reflected from an obstacle reaches the ear after the sound from the source has already been heard. Once the source of the sound initiates something, emits something, you hear it, and then again you can hear it, the same sound again, then that is called the echo. Your ear can distinguish between the original sound and the echo if it is received by your ear after 1/16th of the second. If it is received before 1/16th of a second, then it will be enhancing the quality of the original sound. But since it is if it is received after 1/16th second, a fraction of a second you can say, but if it is received after that time, then it takes a longer time to come to your ear. It is received after certain time, certain minimum time, and then it is called an echo. The related effect is another one, Echelon effect. You may have seen in an auditorium, or you may have seen in the cinema halls, that the sitting arrangement is on stairs. It is a staircase like sitting arrangement, right, on which one can see that there are some carpet materials. Why? Because when such gradually changing surfaces, actually regularly successively changing surfaces are subjected to any sound waves, they will be emitting regularly, and then they will act as a minor source of sound waves, and then they will those sound waves will interfere, and then they will make some points of maximum amplitude, some points of minimum amplitude, and this type of effect is called Echelon effect, right? So it is again the reflection, but it is a successive multiple reflection of sound waves, right? The third reflection is called the reverberation. It is the persistence or prolongation of a sound in a hall even after the source of sound is cut off. One person is speaking, he has spoken one sentence, stopped, and then even after he has stopped speaking, if you have the feel of that particular sound in the room, then it is called reverberation. And reverberation time is the time taken by the sound to fall below the minimum audibility level after the source is cut off. That particular time is called reverberation time, and this reverberation time plays a very vital role in the acoustics of a building, right? It should be optimum enough. It is the time for which the sound exists in a particular room, right? So that means if one syllable is spoken, one sentence is spoken by the person, and then if second sentence is spoken exactly after that, then if first sentence effect remains in the room, then you will feel that some confusing state is there. So reverberation time should be minimum, say optimum enough. It should not be less than optimum, because if it is not sufficient enough, then the last person may not hear it, right? May not listen it. And if it is very large, then it will create some confusing effect between the successive syllables. So reverberation time should be at its optimum level. Now, how can we put the reverberation time at its optimum level? Because we are dealing with the two situation. First is the reflection of sound. Second is the absorption of sound. Now, what is the absorption of sound? The property of a surface by which sound energy is converted into heat energy is known as absorption. It is due to the frictional resistance inside the pores of the material. The absorption coefficient, which is a unique characteristics of any of the material, is the ratio of sound energy absorbed by the surface to that of the total sound energy incident on the surface. The unit is Sabine or open window unit. Now, what is an open window unit? Again, what will be the absorption of any of the material? How will you measure it? Using its absorption coefficient, you will say. But using the absorption coefficient, you will have to find out the energy which is absorbed by the surface, right? Total energy you can always find out, but to determine this absorption coefficient, one has to find out one material which is absorbing the 100% sound energy, for which the sound absorption coefficient is 1, right? With respect to that, you can say that with this particular material, with respect to this particular material, the given substance is absorbing 50% or 75% or something, right? So that can be defined in again a relative manner. Okay, so to define the absorption coefficient, one can take 1 meter square of an open window, which is unit area absorbing everything. Since it is an open window, the sound which is incident on it is 100% transmitted, right? So we are not dealing with any of the transmitted sound. So for us, it can be absorbing 100%. So with respect to 1 meter square open window, we can say that 5 meter square of the given surface is absorbing this much. So that is with the relative absorption measurement, one can find out the absorption coefficient of the material with an open window unit, right? Now Sabine's formula, T is equal to 0.167 V by A, that was discovered by Professor Wallace C. Sabine. He was a professor in Harvard University. He has actually corrected the Harvard University's main music hall in terms of acoustics. And he had actually established the importance of the reverberation time for the study of the acoustics. After his experimental discovery of reverberation time importance, after some 20 or 40 years, Benjamin actually theoretically derived this equation using certain assumptions. First is sound energy is uniformly distributed inside the hall. Second is the absorption of sound by air is neglected, and the third is sound travels uniformly in all directions. So this can be the three assumptions, which is more or less they are actually correct. And these three assumptions, when Sabine's formula is derived, what he assumed one small one on one surface of the room of volume V, he assumed that there is a small surface element ds. On that ds he made one normal which is On here, and also he found the two semicircles which are in perpendicular plane to that ds, and on that, by drawing that semicircles with the radius r and delta r and dr, he found one small surface element, as you can see in the figure. And now when we say that he has moved that particular surface element with an angle d phi along with the normal n, and now you can see that one small volume dv is made by that particular rotation, and this from this particular volume, small volume element dv, what will be the sound energy that is coming towards ds? If with that we can find out, then that will be the total incident energy. By using the sound absorption coefficient of ds, one can find out the absorbed energy, and then we can, using the solid angle from dv, we can have the surface, we can have the energy absorbed by the smaller surface, and then we can just integrate over the volume to have the total absorbed energy by the surface, and then we can sum over all this type of surfaces having different absorption coefficient and having different surface areas. And there are four major steps to calculate this Sabine's formula. First is the calculations of the rate of sound energy inside a hall or a room in terms of energy density E. Second, to calculate the final steady value of E in terms of the emission of power P, and then to find out the rate of growth and rate of decay. And to obtain the reverberation time, that is the equation for reverberation time, 0.167 V. Capital V is the volume and capital A is the total absorption in the room, which can be defined as sigma AI SI. AI is the absorption coefficient of ith material and SI is the surface area of the ith material. Now this is an example, but that can be done using this equation. And the last topic today I can cover is the factors affecting the architectural acoustics, and these are actually very